Okay, so let's what we'll do start with today is the concept of critical Mach number. Okay, now what do we mean by that? Okay, now consider this airfoil, right, and say we have say a Mach number, incoming Mach number, say 0.3, right, and at this particular point, okay, at this particular location, say A on the surface of this airfoil, we have minimum pressure, okay, and hence maximum Mach number, okay, maximum speed, and this for this particular case say is okay. So, so we have an incoming Mach number for this particular Mach number at this point A, okay, at this location A, we have minimum pressure and maximum Mach number, which is 0.435. Okay. Now, let us say we increase this Mach number. Okay. We increase this Mach number to say 0.5, right. Then the corresponding Mach number at this point becomes say 0.772. Okay. So, now if we sort of do a reverse calculation, okay. Now, if we say that the Mach number here is 1, okay. If the Mach number is 1, then what is the corresponding incoming Mach number, okay. So, if the, so what we are doing here is, first we said that we have a location here which is minimum pressure, maximum Mach number, right. So, we have an incoming Mach number which is 0.3, okay. Corresponding Mach number here is 0.435. We increase this Mach number to 0.5. So, the corresponding MA becomes 0.72. Now, we say that okay, now in that case what is the Mach number to induce or to have a Mach number at this location as 1, to have sonic region at 1, what should be the corresponding Mach number. Okay. This is essentially, well, in this particular case this value is say 1, and this Mach number is also called the critical Mach number. So, basically by definition this is the Mach number, okay, Mach number at which sonic flow is encountered first by the airfoil. Okay. Okay. So, now having sort of driven this down here, now if you remember this, the isentropic relationships, okay, isentropic relationships. So, P A, the pressure at A, and this is the free stream, would be given by okay. And also if you remember, the coefficient of pressure is basically okay, and also therefore, let us write coefficient of pressure at the location A. Okay. I can write this as so basically this. So, let me just write that as P A by P infinity, right, minus 1. Okay, I can write this, and P A is, again you can see this, you can write in terms of the Mach number. Okay. So, therefore, if this is the critical Mach, if A then becomes if you consider the Mach number as the critical Mach number, right, then M A becomes 1. Okay. So, when I say that, so if so basically what we are saying is that when this free stream Mach number becomes the critical Mach number, at that point M A, which is the Mach number at the point A, becomes sonic or 1. Okay. So, when the free stream Mach number is the critical Mach number, okay, this implies that Mach number at the point A is 1. Okay. So, if I introduce that here, so let us do that. Okay. Let us do that. So, then P A essentially becomes, this is the critical Mach number. Okay. This goes off. Okay. So, correspondingly, we have this. Okay. So, then also I can say at this point C P A, or this is the critical critical coefficient of pressure. Again, this also becomes critical. Okay. So, this. So, let us call this as, let us call this expression as okay. So, this is what we basically what we mean by the critical Mach number and the corresponding critical coefficient of pressure. Okay. So, so now what we sort of did last time, the last lecture, was first of all the Pranal-Gloat rule, right? Pranal-Gloat rule, which gave us a connection between the compressible flow coefficient of pressure and the incompressible flow coefficient of pressure. So, the Pranal-Gloat rule, the Pranal-Gloat rule said that this is the Cp, right? This is the okay. So, Pranal-Gloat rule, basically what we see over here is that this is the incompressible coefficient of pressure, and this is, so with some corrections to it, we get the coefficient of pressure for the compressible flow, right. Now, we now similar corrections. Now, the thing is that now this coefficient of pressure, coefficient of pressure with some corrections involved, can be then used for with suitable corrections, actually can be used for compressible flows, right. So, I will just write down two of such corrections suggested, and we will see how these look like. Okay. So, this Lighton suggested this, where he considers that the local Mach number. Right. If you see this, basically he considers the local Mach number, not the free stream. Okay. Now, I think the greater question here is, why do we need these corrections at all? Okay. We will just talk about that in a bit. Let us get over with this and we will discuss this. Okay. So, so this is a correction. So, instead of just the free stream Mach number, he uses the local Mach number here. Okay. And if I can relate that using isentropic relationships to the free stream Mach number, and then I get this looks like, if I do that, if I write that in terms of the free stream Mach number, it looks like this. Okay. Okay. So, this is the correction which is suggested by light tone, and there is yet another one which is suggested by Carmen and Cien. So, let us see that. Okay. Okay, and that looks like this. Okay. So, basically, so what we have over here is that this is the Pranal Gloat rule, right, and these are the two corrections which is suggested, basically two corrections suggested by light tone and Carmen and Cien. Okay. Now, now it is important to understand here that if you remember when we started, right, when we started doing linearized linearized theory, okay, and we took small perturbations, okay, we got what was the acoustic equations, right. We got the acoustic equation in which basically we got a wave, right, which was traveling at the speed of sound. Okay. And then we said we will not consider small perturbation, we use the method of characteristics, and then we so basically we try to solve exact equations, and then what we got, that each locally the velocity is different, which is what it should be, right. So, therefore, it is important to consider the local Mach number. Okay. So, it is important to understand or to find out the local properties. So, in this case, which is the Mach number. So, therefore, these corrections are important. So, now if I use this, okay, if I use this, and so what we will do is say do a plot of this. Okay. Now, this with a suitable correction using either of these, the Pranal rule, light tone or Carmen Cien, we will see that we will get a more or less usable coefficient of pressure for the compressible flows. Okay. What I have done here is, again, I have used essentially Scilab. Okay. So, having used that, let me show you this. Okay. Okay. So, what I will do is I will plot this and then I will show you. Okay. So, basically for a series of subsonic Mach numbers, right. So, now if you see, this is the critical Mach number, etc. So, then we calculate the corresponding critical coefficient of pressure. So, here basically I calculated using the equation which I have just developed, right. And doing that, okay. So, now, so this is the Prawn-Gloat relationship, this is the Cp from corrections using from light tone and Cp from Carmen Cien rule. Okay. So, having done that, let us look at the result for this. Okay. Let us look at the result for this. So, if I do this, okay, okay, now let us look here. So, this is basically the critical coefficient of pressure, the blue line. Okay, if you look at this, the blue line here is the critical coefficient of pressure, okay, which I just calculated, and the red line here is doing the same with the Pranal-Gloat equation. Okay. The yellow line is using the corrections of Carmen Cien, and the green is using that of light tone. Okay. So, now if I say zoom into this area, if I say zoom into this area, say, okay. So, any of these intersection points, okay. So, this is the basically the critical coefficient of pressure, okay, incompressible. So, with the suitable corrections, we get usable, coefficient of pressure. So, that will be given by the intersection of these curves, right, as you can see from here. So, that is basically a good way of using, okay, the incompressible incompressible coefficients of pressure, Mach number, etc., to the supersonic to the compressible flows. Okay. Now, also the Pranal rule. Okay. Now, the Pranal rule also has interesting, say, just look at, say, a use of this. Okay. This is the Pranal rule, right. Now, say for example, so we have basically okay. So, say we are considering two Mach numbers. Okay. Say we are considering two particular Mach numbers, okay, over the same airfoil. Okay. So, basically for the same airfoil we will have the same incompressible coefficient of pressure. So, this does not change, okay, but the incoming Mach number changes, okay, which means say at M1. Okay. So, let us call that as Cp1, the corresponding coefficient of pressure is, the incompressible coefficient of pressure does not change. So, we have this. Okay. So, here, okay. So, let us say this, and similarly say at okay, we take another Mach number, which is this, the corresponding coefficient of pressure will be okay 1 minus m2 square. Now, say if I were to write in terms of say m1, okay, is equal to 4, okay, m1 is equal to 4, then Cp4, say m2 equal to 0.75, right, is that Cp for say 0.4, okay, is equal to Cp naught by 1 minus 0.4 square, and Cp at 0.75, okay, is Cp naught by 1 minus 0.75 square. Okay. So, what do we do over here? So, therefore, let us divide the whole thing, right. So, therefore, say Cp 0.4 by Cp 0.75 is equal to okay. So, this is it, or what we can write from here is that Cp at 0.75, okay, so we can basically use the Pranal rule in a manner like this. Okay. So, let us sort of look at a relevant problem, okay, and see what we can do. What I did actually here is that we basically have two Mach numbers 0.75 and 0.4, and you can you can connect the two. You can see you can actually each of these coefficients of pressure individually can be expressed in terms of the incompressible pressure coefficient, right. And if either one, and then also if either one is known, you can calculate the other in terms of each other as well. Okay. So, that is what I am trying to show over here. So, let us look at a problem. Okay. Let us look at a problem, say okay. So, now say we have a consider right a flat plate at an angle of attack of 4 degrees, right. So, then first job is calculate the CL and the quarter chord coefficient of pitching moment, okay, for free stream Mach of 0.03, okay. And the second case is that okay. So, calculate CL and CMC by 4 for Mach number 0.6. Okay. So, so basically we have a flat plate. Okay, we have a flat plate. Okay, we have a flat plate which is making an angle of attack of 4 degrees. So, we want to calculate the CL and CM for a Mach number of 0.03 and at Mach number 0.6. How do we go about this? Okay. Well, Mach number 0.03, we can regard that as incompressible. Okay. So, this particular case, so A, we can say this is incompressible, right. We can say this is incompressible, right. And then if that is so, then your CL becomes 2 pi alpha, where alpha is your angle of attack. Okay. This is a ready-made solution, and flat plate quarter chord, it is 0. Okay. If this is it, okay, then we calculate the CL and CM for Mach number 0.6. How will we do this? Okay. If you remember what we did last time, Pranal gloat rule, it gives us a relationship between the CL and CM of the compressible and incompressible flows as well, right. So, if you remember, so what we had was CL was incompressible CL, right, and right. So, we have a so this is basically the free stream Mach number here is 0.6. Okay. So, we are considering a compressible flow here. Okay. But what we do is we have found out CL and CM for incompressible. So, just using this particular correction, which is the Pranal gloat rule, we shall be able to calculate CL and CM C by 4. Okay. All right. So, basically that is a problem. Now, let us look at another problem. Okay. Let us look at another problem, and which goes like this. Okay. Which goes like this. Now, if you, so basically consider a flat plate, okay, okay, of chord length C, right, and angle of attack is alpha, okay, supersonic free stream, which is Mach number, is this thing, okay. So, using linearized theory, okay, derive CL and CD, okay. So, derive CL and CD. So, coefficient of lift and coefficient of drag. Okay. So, we basically have a flat plate of certain chord length. Basically, you have a flat plate. Okay. This is the chord length. Okay. It is an angle of attack at okay, it is an angle of attack of alpha, and the and a supersonic flow is impinging on this. So, we have a free stream Mach number is supersonic. Okay. So, using linearized theory, we need to calculate CL and CD. Okay. So, now the way I will proceed for this, okay, is doing a just doing a very brief review or an introduction to something called thin airfoil theory, okay, which is incompressible flow over a thin airfoil, which is essentially is thin airfoil theory. So, let me start with that. Okay, we will do the treatise and then we will come back and solve this problem. Okay. All right. So, now what exactly is this thin airfoil theory? Okay. All right. Okay. So, now okay, I am going to draw this in a slightly exaggerated manner so you can see. So, let me draw an airfoil. Okay. Okay. So, I do that and then I draw the camber line of this. Okay. I draw the camber line. This is the camber line, which is essentially the midpoint between the upper and the lower surfaces. And then what I am going to do is draw an axis system. Okay. Let that be that, and let that be this. Okay. That. Okay. So, let us call it that, and therefore, here basically I mean you could have you can have a free stream basically. Okay. It is making say an angle of attack this. Okay. So, now numerically in order to calculate lift, we basically have a vorticity distribution, okay, over this airfoil. So, the way we will go about that is let us just say we have okay, a distribution of vortices which looks like this. We are using this camber line, okay, and distributing these vortices over here. Right, we distribute these vortices and okay, and now this is essentially a we'll just write this, okay. This is okay. Now this surface, okay, this surface, let's just say, okay, say this is S, okay. Now and this the vortices are distributed over this surface, okay, this curved surface which is the camber out here. So therefore my vorticity distribution, okay, if I were to, okay, clean this up a little bit, okay. So then what I will say is my vorticity distribution is over this surface S, okay. So gamma is basically the strength of this distribution, okay. And let's just say the curve out here, okay, this curve is basically given by this, isn't it? And also here let's just say the at any, say, particular point, okay. So this is a vortex sheet, and velocity will be induced by these these vortices onto this at different locations. So at a particular point, say at here, okay, so this is the normal component of the velocity induced, okay. This is the normal component of the velocity induced, and let's call that as, okay. So the reason I show that is that because this normal component is with respect to is on S, yes, on this curve, okay. So on this curve, so we have the vorticity distribution, the vortex distribution on this curve S, okay, the strength of which it is gamma. The curve itself you can write as, say, z is x is a function of x, right, and the normal component of the velocity induced is this, okay. Now we have to satisfy, when we have a distribution like this, we need to satisfy, okay, a condition. Now our objective here, okay, our objective here is to find a suitable distribution of vorticity such that this camber line is a streamline, okay. So our objective is that the camber line is a streamline, okay. So we have to find a suitable distribution of this vorticity such that this camber line here is a streamline, okay. And of course this gamma s, okay, should also satisfy the kata condition, right, which is the necessary boundary condition, which means, okay. Why is the kata condition important? Because it's nature's way of ensuring that the flow leaves the trailing edge smoothly, okay. So that is basically a kata condition. So we have a distribution like this, okay, which looks like this. Now these are the conditions which need to be imposed, right, that the camber line, we have to find a suitable gamma, that the camber line is a streamline, and also the kata condition, right, that gamma the trailing edge is 0. Okay. So now, so this is the airfoil, okay. Now when I started out by saying thin airfoil theory, okay. Now what happens if I consider this as a thin airfoil, okay. Now let me draw this again, okay. Let me draw this again. It's basically the same airfoil that I'm going to replicate here. Hopefully I will be okay. So I'm more or less okay, right. So if I do that, and again I do this, okay, this, and I am again going to draw this. Okay. So, if I this is my axis system. Okay. So, in this particular case, okay, so again this is my S, right, this is my surface, right, and this is the chord length. So, similarly this is the chord length. Okay, now what happens if it is a thin airfoil? Okay, so when we say thin airfoil, okay, so what we mean to say that we are ignoring the thickness, right, or that is to say that this is an airfoil of 0 thickness. Okay, if it is a thin airfoil, then what will happen is that my vorticity distribution is here. Okay. Now, you can consider this basically as, well, not consider, this is the chord length. Okay. This is the chord line, you can consider this as the chord line. Now, if you see the difference, so in here, now this is basically for a thin airfoil. Okay. Now, this is for a thin airfoil, where what we do out here is that I consider I consider the distribution on the chord length. Okay. Now, in here we consider on the chord length, right, and so as you can see here, right, the normal. Okay. So, the normal to this still remains this. Okay. This is the normal. Okay. And this is okay, and here of course, okay, here of course the normal is this. This is the normal component. Okay. So, here, so vortex distribution, what we are basically saying that the vortex distribution on the camber line, okay, is is just the same as vortex distribution on the chord line. Okay. So, for a thin airfoil, what we are saying is that vortex distribution, okay, on camber line, okay, on the camber line is the same on okay, chord line. Now, here, okay, so what we are saying is that the this is my camber line. Okay. Now, the vorticic distribution is on the chord line, okay, unlike in the previous case. Now, the two boundary conditions still have to be satisfied, okay, which is that the kata condition has to be 0, and okay, now the gamma s, now this still remains the same. The in here, okay, although the gamma here, okay, so gamma here, so we can basically say here, okay, so we need to define the strength of the vorticity in this particular case, where still the camber line is the streamline. The streamline is not the chord line. The streamline is still the camber line. Okay. So, therefore, the 0 normal boundary condition, okay, has still to be satisfied over the streamline. okay, although the vorticity distribution here is on the chord line. Okay. So, that is basically the difference, that is basically the essence of the thin airfoil theory, right. So, when I say that, let us go and do some bit of math and see if we can get some equations. Okay. So, in order to do that, okay. So, now again, okay. So, if I were to look at this, okay. So, say I will just draw the camber line here, okay. Let me just draw the camber line here, okay. So, okay, and I will draw the camber line, okay. I am drawing just the camber line here, okay. So, and basically we have this is making alpha, this is the free stream, okay. This is the free stream and or the camber line, okay, the camber line as we have from before, okay. Now, let us consider a point P over here, let us consider a point P, okay, and drop a perpendicular at this point. So, at this point we are going to drop a perpendicular, okay. What do I mean by that? So, what I am going to do is drop a perpendicular. This makes this is perpendicular at this particular point P, okay. So, if I do that, okay, okay. So, now I have this line over here, okay. So, now okay. Now, this slope over here at this point, the slope, okay, the slope of this line, okay, if you look at this, the slope of this line. So, this is essentially, okay, so if you look at this is the slope, okay, this is the slope, isn't it. So, at P, okay, so at the point P, okay, the slope is equal to Tc by Tx, okay, Tc by Tx. So, if I say this is theta, that means that this is theta as well, okay, this is theta as well. So, then if let me consider say the point this as A, okay, and say this point say which is B, okay. So, if I consider this triangle PAB, okay, so if I look at that, so in the say triangle, okay, from there, okay, because this is theta, okay, I am just considering the slope out here, okay. If I consider that and this is right angle over here, okay. So, A B, if you look at this, A B is equal to that and A P, okay, or rather P A to be technically correct is dx, okay. So, therefore, okay, so therefore here, so having said that, therefore tan theta is equal to minus dc by dx, okay. So, the slope out here is basically minus dz by dx. So, actually I should write it this way. Okay. So, again now if you look at this over here, okay. Now, let us include this. Okay. Now, this, okay, I am drawing this line parallel over here. So, this is my angle here. So, this is my free stream. Okay. This is my free stream, okay, and okay, if I look at this, okay, if I look at this, so then this is my alpha. Okay, this is my alpha, and if I drop a perpendicular over here, this is my theta. Okay, this is my theta. So, now basically what I am trying to look at here is calculate the normal component, okay, the the normal component of the velocity in this direction. Okay, so this is the direction that I need. Okay, so this is the v infinity normal component in this direction. Okay. So, basically if you look at this, okay, if you look at this particular triangle. So, let me say in this particular triangle, so say this is say D, E and F. If you look there, if you look there, so in the triangle DEF, what you will see is that, okay, is right, because this angle DFE is alpha plus theta. Okay. So, all we need is the cos is this way and the sine is this way. Okay. So, V infinity sine of alpha plus theta. Okay. So, this is it. Okay. So, now, so this is a normal component which is coming because normal component which is induced due to the incoming flow. Okay. Now, our job here is basically, okay, in order to satisfy the the zero normal boundary condition here, is that we need to find out the vorticity distribution in such a way that we satisfy the zero normal boundary condition. Okay. I think we will start from here in next class and finish up the problem. Okay. We will finish the thin airfoil theory and we'll do that. So, okay, let me at least just say for here basically is that now that we've done over here and we have found out that the normal component of velocity is Vn. So, therefore, total velocity induced at say the point P, okay, is this. Okay, and that total normal component of velocity is 0. Okay. So, what we will do is we will start from here, okay, and complete the thin airfoil theory and then take it from there and finish up this problem. Okay. We will stop here. Thank you.